Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover the 4 laws of thermodynamics. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with the 3rd law, approaching absolute zero. The 3rd law concerns the behavior of entropy as temperature approaches absolute zero. Walther Nernst formulated the original version in 1906, based on careful measurements of the heat capacities of solids and the free energy changes of chemical reactions at low temperature. Nernst's heat theorem, 1906, as the temperature of a system in internal equilibrium approaches absolute zero, the change in entropy associated with any isothermal process between 2 equilibrium states tends to zero. In 1911, Max Planck strengthened the statement. Not merely the change in entropy, but the entropy itself approaches a constant, and for a perfect crystalline pure substance, that constant is zero. Planck's 3rd law, the entropy of a perfect crystalline substance approaches zero as the temperature approaches 0 Kelvin. Equation 12, the limit of SST approaches 0 equals 0 for a perfect crystal. Figure 12, a graph with absolute temperature on the horizontal axis and entropy on the vertical axis. A smooth curve starts at the origin, where S and T both equal 0, and rises monotonically to the right with progressively smaller slope as the temperature grows large. A dashed horizontal line marks S equal to 0 along the axis at low temperature, and a label near the origin reads, perfect crystal. S approaches 0 as T approaches 0. A small note in the upper right reads, entropy S grows with temperature and with disorder. The Boltzmann formula explains why the 3rd law has the form it does. A perfect crystal at absolute zero has exactly one accessible microstate. W equals 1, so the entropy S equals K sub B times the natural log of 1, which is 0. Unattainability of absolute zero. A crucial corollary, sometimes called the unattainability principle, follows from the 3rd law. The unattainability principle. No procedure, however idealized, can reduce the temperature of any system to absolute zero in a finite number of steps. Each cooling step extracts a smaller and smaller increment of entropy from the system, and the increments tend to zero as the temperature falls. Figure 13. Each cooling cycle alternates an isothermal step, in which entropy is extracted, with an adiabatic step, in which temperature drops. As the temperature decreases towards 0, each successive step removes less entropy. So, reaching absolute zero requires an infinite number of steps. Reaching 0, Kelvin would therefore require infinitely many cooling steps. Modern dilution refrigerators routinely reach the millikelvin range. In 2003, Wolfgang Ketterle's group at MIT cooled a sodium atomic cloud to a kinetic temperature of 450 picokelvin, yet absolute zero itself remains a mathematical limit, never a destination. Why does the 3rd law refer specifically to a perfect crystal, rather than to any system whatsoever? What goes wrong in the Boltzmann picture for an imperfect crystal, say a glass that froze with some structural disorder? That wraps up the 3rd law, approaching absolute zero. Next up, Section 6, the laws in practice. If you found this helpful, like and subscribe and support the channel.